these were cells, and they probably don't have positive mental states.
No, I don't know how to measure that, but maybe they do. And so their phenotype, their cell behavior was more in line with a young cell after psilocin treatment.
According to the psilocybin-telomere hypothesis, uh, the way you describe it, I felt like you were saying that telomeres were less shortened over time due to psilocybin in some way dependent on the positive mood effects of psilocybin. And
Sure.
that's probably out of the equation here, right? So maybe there are some independent effects as well.
Yes. So not only do you have reduced oxidant production, but you also have boosted antioxidant responses. And so that net effect is what we measured also, which is just oxidative stress levels were lower. So I guess relating this back to telomeres, do they have less oxidative stress levels because they have more protection of their DNA and longer telomeres? Or is it because you have less oxidative stress, which contributes to less telomere shortening? So I don't know, which happens first and how they are interconnected. But the net effect is you have all of these things happening. And that was probably one of the most striking findings for me is that psilocybin or psilocin seem to act on multiple hallmarks of aging. I think somebody asked me the other day if if I'm going to stay in this field, and if because I've never done psilocybin research before this, and I said I will be doing psilocybin research until the end of my days because it's so fascinating, and I'm just you know kind of obsessed now. So I just but when I always do all my science is I follow the data, and the data is really striking. We know that the mice experienced a psychedelic dose because the mice exhibited what's called a head twitch response, which again, this is something we know from prior studies with mice and psilocybin that when you give mice psilocybin and it's a psychedelic dose, they have sort of this head twitch response, and that's what we showed that, when 50% of the vehicle mice had died, then we only saw 20% of the psilocybin-treated mice had died. But really the most interesting finding, in addition to the survival finding, which is, striking, one of the most surprising findings that we started noticing really early on after treatment that the psilocybin-treated mice just seemed to look better. It was something that everyone in the lab could kind of see, even if we didn't know how to quantify it at the time. And then over time, we noticed that, not only were they looking better or were they looking better than the vehicle group, but they were looking better than at the start of the experiment. So, you know, mice with white hair grew back brown hair in its place, and mice with bald spots grew back hair. So that was something that, was completely surprising to us.
All right, welcome everybody to this episode with Dr. Louise Hecker, who is a scientist who has extensive experience studying the cellular processes of aging, particularly in lung tissue. So some of Louise's previous work has been focused on idiopathic lung fibrosis and cellular mechanistic processes of aging. So rather than coming into this study with a focus on psilocybin or psychedelics, she has more experience looking at aging processes within cells rather than psychedelics. Today we're talking about the potential effects of psilocybin on aging. Now, Dr. Louise Hecker has been a researcher at Emory University. She's not there currently. But so the study started at Emory University and was funded by Emory University. But then Dr. Louise Hecker moved to Baylor College of Medicine. And so the final analyses of the data were done there. The study was published in the Nature Partner Journal of Aging, and the title was "Psilocybin Treatment Extends Cellular Lifespan and Improves Survival of Aged Mice." And so I find this very interesting. Like the first time I saw this, I was just, wow, that just happened. That was published in Nature. That's just mind blowing. That yeah. Um, and so I find this study fascinating. I find the results fascinating as well. And so I think that you'll find our discussion fascinating as well. And yeah, and so I welcome you to enjoy this conversation as much as I did. And so here I bring you Louise Hecker on the effects of psilocybin on aging. Louise, would you like to tell the listeners and me what sparked your interest in this field of aging and particularly in well, psychedelics and how they might impact the processes of aging?
Sure. Well, thanks for having me on your show. And yeah, this is uh, a good story, actually. The whole story really started with a friend of mine, Aaron. We used to work out religiously together on our rooftop of the building I used to live in, and he's a smart guy. He's not a scientist, he's an attorney, and he was, I like a lot of my non-scientist friends, they're always asking me science questions, and Aaron is always asking me about psilocybin. Um, Aside from the basics, I really didn't know anything about psilocybin, and so I finally, after him asking me enough times, I said, "Well, let me just read about it." And I started reading, and within, the 15 minutes, I was just kind of hooked. I mean, I just wanted to keep reading. I was kind of, you know, blown away by how much data there was on clinical trial information that, when I was reading then, there were at least 150 plus clinical trials ongoing or prior
Yeah.
that, had looked at psilocybin for so many different disease indications and showing so much clinical efficacy. Um, and so that was kind of mind blowing. Like, how many different drugs can you really think of that work on so many different disease indications? So I found that interesting. And then I also realized that really everything, or the overwhelming majority of what we know about psilocybin, was clinical outcomes that had been reported from these trials, or what was known about its impact in the brain. Aside from that, very little is actually known about it. And so I was also kind of intrigued by the fact that this compound, this drug, does so many things, but yet we really don't know a lot about what it does outside the brain. And I came across this one uh, paper, which was a medical hypothesis called the psilocybin-telomere hypothesis. And it was somebody's idea, that was based on a large body of data. It's a theory, if you will, that you know, positive psychological states are associated with longer telomere length, and negative psychological states are associated with shorter telomeres. So the idea that he put out there was maybe the way working on all these different diseases is doing something to telomeres, which telomeres are a hallmark of aging. Um, and shorter telomeres, something that happens with normal aging. Um, so I thought to myself, I can test this. I study aging and age-related diseases, and so, this is something that I can test, and that's kinda where it all started.
Yeah. Yeah. Cool. Nice story that you were doing exercise with your friend there and just followed your interest
Yeah, yeah.
and you went down the rabbit hole essentially.
Yeah,
Yeah.
I mean, it's things like this that really make me feel proud to be a scientist, right? Because this is why I became a scientist, that I could come up with some, random idea and then go into the lab and test it, and that's exactly what I did.
Yeah. Yeah. You mentioned that the telomere, psilocybin-telomere hypothesis. Is that it?
Yes.
Yeah. And so I have a few questions about that. Um, so the hypothesis is that psilocybin induces positive mental states, and that positive mental states reduce the length or preserve the length of the telomeres so that they don't get shorter as quickly.
Right, right. So to kind of back up so that everybody understands telomeres. So telomere, I like the analogy of telomeres are similar to like that protective cap on the end of your shoelace. It's it's nice and defined and uh, intact when you first buy those shoes, and then as you wear those shoes, that end of that plastic cap kind of starts to fray and and shorten, and that's exactly what sort of telomeres do on DNA. They're the protective caps on the ends of your DNA, and as our cells divide, those telomeres slowly start to shorten until the cells and exposing DNA to damage and until the cells can't divide anymore. Um, so so the idea was that, yeah, because psilocybin is known primarily from clinical trials to cause or to impact or lead to better positive psychological states, that maybe the way that it's doing that or a mechanism is that it's impacting telomere length and aging process.
Oh, okay.
Right.
So the idea is really in the opposite way of what I was thinking, because I was thinking that maybe the positive psychological states could impact the telomeres, but you're saying that the telomeres could be the mechanism for how the positive psychological states are biologically induced.
Potentially, yeah, or potentially, yeah, it's preserving that telomere length.
But so you measured fibroblasts in this study, right? And human fibroblasts of the skin and of the lungs. And what you found is, well, can you describe what you found as regards? Let's start with the telomeres. Continue there. Yeah.
Okay, so maybe I should explain the cellular model. Uh,
Sure, sure. Do that first. Yeah.
so and a lot of people keep asking me like, why did you use lung cells and skin cells? The reality is those are cells that I work on, so I had them in the lab. One, two, there's models of there's a model of replicative senescence, which is something that is a well-validated model. We don't want to reinvent the wheel. We want to study cellular aging in a model that's already a well-accepted, established model of cellular aging. And so the way that you study that in cells is that, cells can only divide so many times. As we know this from the Hayflick limit. There's a limit to the number of times cells can divide. And so normal cells will start out very proliferative and then they sort of peak. And toward the end of their cellular lifespan, they just kind of poop out and stop. They become senescent and they stop dividing.
Mhm.
And so essentially we can kind of monitor this normal curve where cells kind of proliferate quickly, it is kind of slowing down and then plateau, they stop dividing. And so what we did was we gave cells vehicle or psilocin, and I say psilocin is the active metabolite of psilocybin. So when you ingest psilocybin, it's metabolically, it's broken down through the digestion process and metabolized, and the active metabolite is psilocin. So what your body sees that, is the active metabolite, which is called psilocin. So we treated cells with psilocin over the course of their lifespan or vehicle. And what we found is that, where normal cells were kind of pooping out, the psilocin treated cells were growing faster. They were able to divide quicker. They were able to divide more times. They were able to live longer. And then they did eventually poop out, but much later. They were able to live a lot longer, up to 57% longer. And this was dose dependent. So you give less psilocin, they have increased life extension, but the higher the dose, we saw the greater the life extension. So that's kind of the main finding in terms of cellular life extension. And then we sort of started breaking down, well, how is this working? Um, Telomere length is a big hallmark of aging. That sort of normal wear and tear, like the shoe leaf cap, happens with aging. And so we thought, let's measure telomere length. And so what we found is that the length of those telomeres was actually preserved in the psilocin treated cells. So where it had naturally shortened the vehicle treatment group, the tumors remained long and preserved in the psilocin treated cells. So that means they have a little more, that's a mechanism that they can have more DNA protection throughout their lifespan.
Right. And telomeres consist of DNA as well, right?
Telomeres are like the caps on your DNA.
Yeah, but they are like DNA as well, right?
Yes.
Like they're the end of the strings,
Yes.
right?
Yes.
Yeah. Um, and so like because what is replicated during the cell replication process is DNA, right? And so I'm wondering, does telomere length in any way relate to the uh, replicative senescence delay that you saw?
Yeah, yeah, because when they shorten and the telomeres shorten to a certain extent, that's when the cells are unable to continue dividing. So, so having that longer telomere length is in part how the cells can continue dividing.
Yeah. Yeah. Interesting. Okay. And so these were cells, and they probably don't have positive mental states.
No, I don't know how to measure that, but maybe they do.
Yeah. But so maybe
So
then,
what we call phenotypes, right? So they have phenotypic behavior. Uh,
yeah.
and so their phenotype, their cell behavior was more in line with a young cell after psilocin treatment.
Yeah. Right. Right. And so the phenotype is more in line with the young cell, but according to the psilocybin telomere hypothesis, uh, the way you describe it, I felt like you were saying that telomeres were less shortened over time due to psilocybin in some way dependent on the positive mood effects of psilocybin. That's
Yeah.
probably out of the equation here, right? So maybe there are some independent effects as well.
Yeah, so one of the things that's tough to answer right now, so, we looked at other things too, like oxidative stress, right?
Yeah.
So I happen to be an expert in oxidative stress. So that was one of the first things I looked at, and, oxidative stress, a good analogy for that is like it's like rust to the cells, yeah.
Mm,
Oxidants are highly reactive,
yeah.
way you kind of rust with how things age when you leave them outside. And so as we age, we get more and more oxidative stress. That's just something that accumulates with normal aging. So I tested and saw that psilocin led to significantly reduced oxidative stress levels. And if you look at the psilocin treated cells that are aged, they have almost lower oxidative stress levels than even young cells.
Hmm.
So it was and so one of the questions that I don't know how to answer yet is, is the psilocin directly acting on the telomeres, or is it these other things? Like if you have less oxidative stress, that can also contribute to preservation of telomere length. So
Mm,
what it's doing directly and what the downstream effects, that's what needs to still be teased out. And the interplay of those things, where it's acting directly, we don't know because I just took like a snapshot. This is what they look like, right? So,
yeah.
so what it's doing directly, and then the downstream effects of that, and how it plays into the other pathways. That's something that we still need to tease out.
Right, right. But as you mentioned, you did look at the effects of psilocybin or psilocin on oxidative stress processes in these human skin and lung fibroblasts. So can you describe what the effects were
Sure.
of
So
psilocybin.
so I study, and I spent a lot of my career studying an enzyme called NOX4. And NOX4 is like the master powerhouse for oxidant production. And so we saw reduced levels of oxidant production by so the reduced NOX4. And then we also looked at NRF2, and NRF2 is the master regulator of antioxidant defenses. And so we saw highly elevated NRF2. So not only do you have reduced oxidant production, but you also have boosted antioxidant responses. And so that net effect is what we measured also, which is just oxidative stress levels were lower. So I guess relating this back to telomeres, do they have less oxidative stress levels because they have more protection of their DNA and longer telomeres? Or is it because you have less oxidative stress, which contributes to less telomere shortening? So I don't know, which happens first and how they are interconnected. But the net effect is you have all of these things happening. And that was probably one of the most striking findings for me is that psilocybin or psilocin seem to act on multiple hallmarks of aging. So oxidation,
Mm.
telomere length, DNA repair, things like that.
Yeah, yeah. So, well, did it point always towards the direction of less aging, psilocin in these fibroblasts?
Yeah. Um, so I mean, as scientists, we kind of always draw from what we know, right?
Yeah, yeah.
So in that I study age-related diseases, and in all of my projects and everything that I do is really some aspect of aging, age-related repair, injury repair, age-related disease. And so essentially, I took everything I knew from what I've studied and I looked at it in this model, in the context of psilocin, uh, in this cellular model. And every single marker that I looked at went in the right direction, meaning the psilocin treated cells had all the markers that young cells have and seemed to have, none of the typical markers that typically change with aging didn't seem to happen or happened, to a lesser extent. So I'm sure there are hundreds of other things that we can look at, but I just kinda used all the tools that I had at my disposal, that the things that I
Mm.
to look at in through the other projects that I work on, and everything, I mean, everything seemed to be going in the right direction, as in the psilocin treated cells appeared to have sort of a younger phenotype.
Yeah, yeah. What do you make of that? Like, it seems too good to be true almost.
I mean, you know, it was honestly shocking. I mean,
Yeah.
I wasn't. I think when I started this process, I really, like I said, I was kind of blissfully ignorant about, what it takes to study psilocybin. So, normally, if I wanna study something, I'll just walk in a lab, I'll order a drug, and I'll have it that week, and I'll start the experiments. I say blissfully ignorant because I about psilocybin because, um, had I known what I knew what ultimately ended up happening, which is that there are so many regulatory challenges and restrictions to studying psilocybin that I had no idea about. So, I went
Right.
into lab and I tried to order psilocybin, and I realized, "Oh, I can't order psilocybin. It's a Schedule I drug."
Right.
Uh, so you have to go through this whole process of getting a DEA license and, setting up all of the regulatory, procedures and protocols necessary. You have to have it stored in a lockbox inside of a locked box behind a locked door, and you have to have
Really?
DEA inspection, and if anything touches it, like cells, we have to take that and send it to a reverse distributor to destroy it. So you can't just throw it down the drain. And so you have to have all of these things in place before you even can bring it into the lab. And so it probably took from idea conception to actually doing the studies, um, close to 2 years, a year and a half to 2 years before I had psilocybin in my hand in the lab to start doing research.
Oh,
Yeah,
and then probably a year or more for the study and the analysis and the writing and so on.
absolutely,
Yeah.
absolutely. Yeah, yeah.
Hmm.
It was a long process to test this off the wall idea. Um, but after I kind of started the process, was like, well, I've got to keep going. so
Yeah.
so
Yeah.
then we finally got the initial round of data in cells, and it was, just mind blowing, really. Like I said, everything that I knew to test was working. And so that's really what gave us the drive to and motivation to really take this to the next step, which was testing in animals.
Right, right. And we will for sure go into that study as well. You mentioned that the replicative senescence of these fibroblasts it was delayed.
Mhm.
And so when cells keep dividing and divide more and more, as you saw in the study, the direct thought for me is, well, if that's uncontrolled, that could lead to cancer potentially.
Exactly. Right.
But you did control for this in this study.
So in the cells, and again, I think you're bringing up a really important point of, something that we absolutely need to do a lot more research and study is the potential for cancer risk, because when your cells are dividing more, that's exactly the number one risk factor that you have to kind of keep an eye on. That said, in the cells, we didn't see any evidence of what we call oncogenic transformation. So cells that become transformed or cancerous, they that the characteristic of those cells, they continuously divide, uncontrolled cell division. That is cancer.
Hmm.
So, in this case, and we did this study with 2 different cell types at various doses, we saw no evidence of that because, cells always did poop out and stop dividing. So we didn't see any type of uncontrolled cell division. It's just that process of when they slowed down and, stopped dividing was delayed.
Right. So these cells did eventually die as well.
Yes.
Yes.
Mhm,
And
yeah.
it was up to 57%, you said
Up
later.
up to 57%, what we calculate as cellular life extension, and that's based on
Yeah.
population doubling time, how long it takes them to get to that point of replicative senescence, which is when, that upward curve of proliferation plateaus, and
Hmm.
they don't divide anymore, so there's no more cell growth. They're just there.
Yeah. And did the effects differ between the cell types? So lung and skin fibroblasts?
So, yeah, we did not see any major differences. In fact, that was, I think part of the exciting part is that in 2 totally different cell types, and, I'll mention one important difference is that the lung fibroblasts are fetal lung fibroblasts, so they are more kind of pluripotent. They're kind of, they're from fetal tissue. So those are kind of younger cells versus the skin fibroblasts were from an adult donor skin fibroblast. So they are adult mature cells. So that's one difference, which in the different, along with the fact that one is a fibroblast from the lung and one is a fibroblast from the skin. Um, Nonetheless, we saw identical results essentially in both cell types. So the next, one of the things that we would like to do next is, do we see the same thing in epithelial cells and endothelial cells and, immune cells and
Yeah.
all different cell types that we can evaluate?
Will you study neurons?
I won't because I think that that's something that's already or we already know a lot about psilocybin and neurons and in the brain. So I'm trying to kind of open up a new area and look at things that people haven't looked at. So,
Yeah.
really kind of focused on systemic effects of psilocybin.
Yeah. And I think it was like a factor of 10, right? That the different doses is
We did
different doses varied.
micromolar and 100 micromolar,
Did you say 10 and 100?
10 and
Yeah.
100. Yeah.
Yeah. Um, how large were the differences in life extension?
I want to say, and I can't remember off the top. Let's see, at the top of my head. Oh yeah, it's here. I'm looking at the paper. So with 10, it was 30. Let's see, it was 29% life extension versus 57% with 100.
Hmm. So not proportional. It's still quite a relatively large effect then from 10. Yeah.
Yeah. Oh yeah. Yeah. I mean, with 10 micromolar, which is, and we did, and if you look at in the paper, I have, I don't show all of, we had to put a paper out with kind of the most robust data we had in telling the story, but I did show some data in the paper with the oxidative stress levels, and we went from like point zero one micromolar all the way to 100. So even at point zero 0.01 micromolar, there's a significant reduction in ROS levels. So now we didn't look at life extension, y- you know, with every single dose to that extent, but in terms of quantifying life extension, because it's actually an involved process to quantify life extension. It takes several months, and someone has to count cells and split the cells twice a week and treat, and so it's actually a very involved process to quantify life extension over the course of 3 months in cells. Um, so we didn't show all of that data, but we do have some data that we did present showing, lower doses have an effect on, for example, ROS levels. Yeah.
Interesting. Interesting. Yeah. I'm trying to get an understanding of the doses, in part because I want to understand, are these doses that are proportional to the doses used, for example, in clinical trials for various psychiatric disorders when psilocybin is used there?
Yeah. So, well, I can more speak to that if we're talking about the mouse study. Um,
Okay.
so,
So how about the cell study first though? Like
well,
you can't you
I'm not
it's hard
sure
to translate.
qualified to comment on like how a cellular dose systemically in your body after it's been broken down
Yeah.
to the actual, parent compound that you're given in a clinical trial. I'm not sure that I'm qualified to make
Okay.
extrapolation, but
Yeah. But that is an interesting question though, right? Like clinically for the translation. Yeah.
yeah, yeah, I think, more importantly is really sort of the breakdown and of how you design the animal studies because it's, you know, there are different things that you have to take into account when you think about a human person in a clinical trial like metabolism
Yeah.
and um, pharmacokinetics and how it's broken down and so yeah, it's tougher I think to extrapolate from cells to humans versus from animals to humans dosing. Uh, that said, I think the goal for us with cells was to show dose dependence. Do at lower doses you get, when you increase the dose, you have a greater effect, and that's really what we were looking for. Is this dose dependent? And the answer is yes.
Right, right. And the reason you were interested in that is because it's a stronger case than if you found that and you did that it is causal, the relationship between psilocin and these cellular de-aging effects.
Mhm, mhm. Right.
Yeah, right. Um, and so we've talked a lot about the effects of psilocin on fibroblasts. I was reflecting about this, and I recall from our gastroenterology rotation in med school that we were talking a lot about liver fibrosis as a hallmark of liver aging, essentially.
Mhm.
Um, And so I wanted to ask you, do you think that these fibroblast longevity effects essentially might in some way translate to the acceleration of the fibrotic processes on an organ level in humans?
Right. Well, okay, one thing, because I study fibrosis, so, that's kind of one of my main area of expertise. So one of the things that you have to remember about fibroblasts and fibrosis is that, fibroblasts are in most all tissues, and they are they're good in a sense, right? It's only when they become pathologic or they transform, they differentiate into myofibroblasts, and even that can be a good thing. Like if you fall and scrape your knee, uh,
Yeah.
the cells that will come in, you first line of defense is your immune cells, and then next come your fibroblasts, and
Yeah.
they're become activated into myofibroblasts, which are muscle like. They turn from this kind of normal cell into a more muscle like cell, and then that's needed so that they can pull the wound closed
Right.
matrix, and so a normal level of this differentiation between fibroblasts and myofibroblasts is healthy because you need that for natural wound healing and repair.
Mm.
But when you have uncontrolled uh, accumulation of those myofibroblasts, those scar generating cells, that's when you have pathological conditions. And so in disease, you have this massive accumulation of scar tissue, and that's from the inability of these myofibroblasts to stop that process, and they continue to accumulate and generate scar. So, um, now I don't know the answer of because I didn't look to see how is psilocybin impacting, does it impact fibroblast to myofibroblast differentiation? That I don't know. That's definitely something that I'll be testing, being that I'm a fibrosis person, but we actually didn't test it in this study.
I see. Yeah. Yeah. Does that differentiation have anything to do on a mechanistic level with the senescence transition? Because that's also a cell fate, right, of fibroblasts. And
Yeah, so, all cells will become senescent at some point. Um, Myofibroblasts, so actually one thing that I've published on before is um, that that myofibroblasts are actually extremely plastic cells, meaning, we've published that they can actually differentiate into these scar generating cells, and then they can actually de-differentiate back into their fibroblast precursor. But in pathological conditions and with aging, where we found that those myofibroblast cells are kind of stuck in that myofibroblast phenotype and they can't differentiate back into their precursor. So
mm,
be curious to see if, one, does psilocybin have any impact on this differentiation at all? And two, does it assist with the level of plasticity that, even if you did differentiate them into myofibroblasts and you treat them with psilocybin, does it impact their plasticity in aging? That'd be something I could easily test, but haven't tested yet.
yeah, yeah, I agree. It's interesting for sure. And myofibroblasts then like because fibrosis is a quite um, a quite non-replicative tissue, right? Isn't it?
Well, I would say you have this proliferation of these fibroblasts, which then differentiate myofibroblasts. And then,
Yeah.
my research shows that the inability of that, this sort of activated state of these myofibroblasts is what leads to pathogenesis. And so there are lots of ways that can happen. One is that they become resistant to cell death and they stay alive and they keep generating scar. One is that we've also shown another contributing factor is, like I said, this inability to differentiate back into their precursor. So it's really the persistence of this cell type, and that's the key difference between pathological fibrosis, which tends to happen in the context of older age more, versus kind of um, healthy reparative fibrosis, like when you fall and scrape your knee.
Because those myofibroblasts can differentiate to fibroblasts again.
Right. The question for me would be, could psilocybin could psilocybin influence the plasticity of those cells? Can it help them to go backwards so that they are not there accumulating? That would be an interesting question in the context of age-related disease. We're showing this delayed aging because we started the treatment in cells from, from the start of the experiment. But, another question that still remains to be answered is, you know, what if you start with old cells and start treating them with psilocybin, or cells that are really close to approaching the end of their life, and if you did this experiment, where you start your psilocybin treatment at different points in your lifespan, at what point is it not efficacious and provide this benefit of life extension? And at what point, uh, you know, again, this experiment is done where from the start we gave them psilocybin or vehicle. But what if halfway through or three-quarters of the way through their life or the last, you know, toward the very end of their life, we still impact that life extension and how much? And is it less than if you started them from at the start of the experiment?
Yeah.
So we don't know the answer to any of that yet. It's to be tested. I think somebody asked me the other day if if I'm gonna stay in this field and if, because I've never done psilocybin research before this. And I said, I will be doing psilocybin research until the end of my days because it's so fascinating and I'm just, you know, kind of obsessed now. So I just but when I always do all my science is I follow the data and the data is really striking. Frankly, I hope that other people are reading this paper and that they infuse their takes and that they start testing in the ways that they think. And I think that's what makes great science is when people like, for example, this. I mean, I have no background in psilocybin, but yes, I study aging. I saw this idea somebody had and I thought I can test it. And I think those kinds of things make for the best research because I'm coming at it from a totally different angle, looking at something that no one's ever looked at, studying the things that I just know how to study relating to aging. And so I hope that when people see this article come out, that they take their expertise and they apply what they know and they test in the models that they work with, and that we see a lot of new and exciting research coming out of this initial finding.
Yeah. I hope so too. Let's move on to the mice study. Um, so you mentioned this interest of measuring what might happen if you give psilocin, or in this case, in the mouse study, psilocybin, to older, well, you mentioned cells, but in this case, you measured the effects of psilocybin in older mice, right? So 19-month-old mice, which corresponds to around 65-year old humans, right? So my first question about the study is, why did you choose this age and why not younger?
Yeah. So, after seeing the cell data, our goal really was to come up with the most clinically relevant experiment possible. And so what does that mean? Well, it means thinking about dosing. It means thinking about, how this could realistically work in the world. I'll also mention that, and Emory was very generous in funding this because I had applied for many grants, federal grants that just kind of got blown out of the water. And not funded. And Emory had these two pilot grants that really enabled all of these studies. So they were and one of them was for the mouse study was a sort of high risk, high reward grant mechanism, like very looking for very bold ideas. And it was a pilot grant. And so we didn't have unlimited amount of money. We basically had one shot to do a big study and, you know, And so we spent a lot of time designing that study. And so in part, we thought, okay, if we're thinking about this as a geroprotective agent, something that can promote healthy aging in older age, then, we wanted to start with older mice. I mean, I don't think it's super clinically relevant if we start with mice that are equivalent of a 10-year-old and give it for the rest of their life, because I know I know any mother that I know would not wanna start their child on a psychedelic at age 10, but I think as we age, as I age, and, we start thinking about anti-aging more and more and more, and so when you're 65, you're really thinking about how do you live healthier longer, and so that's why the motivation to start with a cohort of mice that were equivalent to, 60 or 65-year-old person that might really be thinking about how do I live healthier longer. Um, in terms of the dosing, we spent a lot of time thinking about the dosing. So um, we have one of our co-authors on the study, Ali John Zarabi. He's a clinician and he has done clinical trials with psilocybin, most recently with these demoralized cancer patients with chronic pain. And so we kind of drew from what we knew about clinical studies that have occurred in his studies, and we tried to kind of identify a dose that was somewhat similar to what's been given clinically. That said, there are other factors, and a lot of people have been asking me about dosing. There are a lot of factors that played into the actual doses that we selected, which include prior mouse studies, all of the clinical studies that have gone on. We also considered a really important factor that went into our decision for dosing had to do with the pharmacokinetics psilocybin in mice versus human. Because I think one thing that if people were to kind of looking at the dose directly that we give mice and then the dose in humans, I think a lot of people might come to the immediate conclusion, well, this dose in mice is way higher than what's given in clinical trials. And I would agree with that. But what they're not factoring in is that mice have much, much higher metabolism than humans. And so as a result, the pharmacokinetics, meaning the half-life of the drug, is much, much shorter in mice. And so we also took that into account, the pharmacokinetic profile, which we actually know from published studies on psilocybin in mice and humans. We know about the pharmacokinetics. And so to account for the much, much higher metabolism, faster metabolism in mice and the shorter half-life of the drug, we actually gave a slightly higher, we factored that into kind of the dosing regimen.
Yeah. And you also gave these doses, well, you first gave a low dose and then you gave high doses monthly as well. Can you elaborate on why you did it that way?
Yeah, so, well, one is there aren't a ton of studies in mice with dosing and psilocybin. There are some, of course, but it wasn't like we had 100 studies to pull from and understand, we did have some pharmacokinetic information from prior studies in mice, but, uh, we started with a dose that we wanted to give a psychedelic dose. So we started with a dose of, I think it was 5 mgs per kg, if I remember correctly. Um,
That's
and
correct. Yeah.
and so that is a dose that we knew that mice would tolerate based on prior studies, and we knew that it should give them psychedelic effects. But so it was kinda like an acclimation dose. We wanted to just make sure there were no adverse effects or that the mice were tolerating the drug well, and then since we saw that everything looked okay, there were no adverse effects, there were no mortality, the mice appeared, you know, to have no, uh, adverse effects in any way after the first dose, then we moved to the higher dose. And then we continued to dose the mice once a month for the next, a total of 10 months.
Right, right. We were talking earlier about whether to call this episode psilocybin well, extends lifespan in mice, and but you thought that no, it's better to call it uh, improves survival. Uh,
Yeah.
Can you explain why you think that's better?
Yeah, and one thing, that again that I didn't realize when I got into this was I just really didn't understand kind of the regulatory challenges with psilocybin. And this is a great example because if I wanted to do the study that I had planned, then I would have given psilocybin starting at the same time when the equivalent of mouse, human age 65. And then I would have followed them for the rest of their lifespan. That's what the study I proposed. Um, the challenge that I encountered was that, all of our animal studies are governed and monitored, and we have to submit protocols to the IACUC, which kind of decides what we're allowed to do in these types of studies. And that is composed of a huge group of people that have all different types of expertise, from veterinarians to even general public to scientists. And so they weigh in on my design, experimental design, and they tell me what I'm allowed to do and what I'm not allowed to do. And ultimately, this was a a study that was really challenging to get approved. Number one, they would not approve a maximal lifespan study. Because at the time, if you think about it too, I mean, this is Schedule One drug. I'm proposing to give it to the mice for the rest of their life at a high dose, and there's absolutely no evidence in animals at the time that
Mm.
this is gonna work, and so they thought, "We're not going to prove that." So they would not approve that, but what they did approve was they said, "Okay, well, at some point, mice are going to age, and there's kind of a median life expectancy, so when any given group reaches 50% mortality, that's going to be the end of your experiment." So technically, I was not given permission to evaluate lifespan extension in the mice because the IACUC determined that they wouldn't approve that. But they would approve a study where I was able to give it to the mice for 10 months, and that if any one group reached 50% mortality, then I should have my answer about whether this impacts the survival, which suggests that it impacts longevity or life extension. So, I mean, when you see these dramatic increases in survival, I mean, I'm going to assume that that will also translate into lifespan extension, but we couldn't actually test that. So that's why the wording is becomes important when you say it didn't really extend lifespan because I didn't actually get to test that.
I understand, yeah. And so their implicit statement or assumption was that, well, this is a Schedule One drug. It might even be dangerous or hurt the mice or lead to suffering and so on.
Right.
And so we can't allow you to continue to expose them for this potentially dangerous chemical beyond 50% of the mice dying.
Right, right. This, yeah, and again, keep in mind that at that time there was no experimental evidence whatsoever, aside from our unpublished data in cells, that it has any impact on life extension. So they were cautious. Maybe this isn't the right study to start with. You should start with this study, and you should have an answer because after 10 months of treatment, and 10 months later, the mice in the control group should reach 50% mortality, or at whatever point they reach 50% mortality, that's when you'll have an answer of if it's changing, improving survival or not. And so that's what we were approved to do, and that's what we did.
Right, right. And can you explain the details of the results?
Yeah. The results are pretty simple. Essentially, we, just gave the mice the psilocybin um, via oral gavage. So we treat with, orally basically. And so we know that the mice experienced a psychedelic dose because the mice exhibited what's called a head twitch response, which again, this is something we know from prior studies with mice and psilocybin, that when you give mice psilocybin and it's a psychedelic dose, they have sort of this head twitch response. We monitored the mice with GoPro cameras above, so we actually have all the data for that. We didn't quantify it because I don't think it was necessary. Other studies have shown that these doses and higher will elicit a psychedelic effect, and then saw we could quantify the head twitch response versus vehicle, but it really wasn't necessary because, and we have the data, so we still can go back and do that. But given that other people have shown these doses lead to psychedelic impact effects in mice, we were pretty confident based on what we were seeing in the mice and what other people have published that this was a psychedelic dose. And then we essentially just started treating the mice once a month, and we're following their body weight, monitoring. Had to monitor the mice very closely, of course, to look for signs of adverse effects. And essentially, the main endpoint was survival. So we're just monitoring because as the mice get older, they're just going to die of older age, and so we're really looking for changes in survival. And that's what we showed that when 50% of the vehicle mice had died, then we only saw 20% of the psilocybin treated mice had died. But really the most interesting finding, in addition to the survival finding, which is, striking, one of the most surprising findings that we started noticing really early on after treatment that the psilocybin treated mice just seemed to look better. It was something that everyone in the lab could kind of see, even if we didn't know how to quantify it at the time. And then over time, we noticed that, not only were they looking better, or were they looking better than the vehicle group, but they were looking better than at the start of the experiment. So, you know, mice with white hair grew back brown hair in its place, and mice with bald spots grew back hair. So that was something that, was completely surprising to us. If I were to do this study again, which I'm sure I will to some extent in a different way, I would definitely bring in a collaborator that knows how to quantify those types of characteristics because I just don't do that kind of research. And at the time, the best thing I had was photographic evidence. You know, so
Yeah.
I can show pictures and say, "Hey, look at this mice 10 months earlier. It had a bald spot that's now gone, and look at this one with." And to me, that's the best evidence I could provide at the time. So one thing that I think is interesting to think about is um, because I've been asked, well, does it slow aging or does it reverse aging? Certainly, our data suggests it slows aging, but and I don't know the answer to does it reverse aging, but I will say that the fact that bald spots grew back hair and white hair turned brown again does kind of suggest that it may do something to reverse aging potentially.
Hmm. And those cells are also of other types than fibroblasts as well, right?
Sure, yeah, yeah.
Like the hair
Mhm.
hair cells, yeah. Do you think that these studies would be replicated, or that these findings would be replicated if you did a similar study again? Do you think that the did you have such detailed control over all the relevant variables that the exact results would likely be replicated, or do you think that they could vary if one replicated the same study design?
Yeah, I mean, I think even if I mean, this has been shown, if you do the same study at one university and another university and the different animal care facilities, even though everything is supposed to be identical, there's always some slight differences. And a lot
Mhm.
of studies actually do that, where they have 3 different sites and they're doing the same study. And overall, they have the same, if the finding holds up, they should have the same general finding. There are sometimes and you can see this in published studies, slight differences from site to site, and we don't really fully understand the differences. Especially, I know from my own experience that with doing aging studies, for example, with aged mice, just in general, we find, and I'm not talking about this study, but in my other research, we found that uh, a lot more variability with each mice. So if I do the same study with young mice 10 times over, the error bars are very tight. If I do the same study age mice 10 times over, the error bars are always much larger, even though I'm doing the same study in the same lab with the same variables. So I think generally speaking, age mice inherently studies with age mice inherently have more variability. So that's one thing to consider, but I also think, people design studies and do studies always with slight differences. Um, so it just depends. But I think the main finding, I am sure will be replicated.
Yeah, that was what I was kind of asking, like how confident do these results make you that these are uh, true biological effects? And it sounds like they make you confident.
I couldn't be more confident. I mean, it's
Mm.
my work, so I'm biased, but so I certainly believe in the findings, but like as I mentioned with the cell data and with the animal data and with all the data that I've seen from this study, that it's so striking that it's there's no question in my mind that this will be replicated.
Yeah, and one of the commonly studied pathways in aging research, to my understanding, is metabolic pathways.
Mhm,
And like oftentimes, if animals are, for example, obese, then they will age faster.
mhm.
Do you think that differences in caloric intake or expenditure could account for part of the, well, survival improving effects of psilocybin in these mice?
Sure. Well, we know that it's very well studied that caloric restriction, is an anti-aging measure. That's been well studied. But that said, there were no differences in body weight really between the treatment groups. The body weights were relatively stable in both groups across time. So there's no evidence or indication that there are any differences in caloric intake um, or differences in body. There were not any significant differences in body weight changes from group to group. So from my standpoint, there's no indication of that in this particular study.
Did you assess and did you find any differences in cause of death between the control group and the psilocybin group of mice in this study?
Yeah, so nothing we could um nothing that was, and again, when I say nothing that was obvious, but um these mice are essentially dying of old age. So, we did try to do some, whatever we thought we could do, like kind of pathological assessments of mice as we could. Sometimes the mice die in the middle of the night and, they animal care removes them so we don't see the mouse afterwards. So we weren't able to catch and do pathological assessments on every single mouse. Uh So, I can't really answer the question. I guess we don't have kind of, quantitative data. We did do some kind of assessments at the end of the light at the end of the experiment, kind of looking to see are there increase, like, is there any differences in, like, tumor growth? And when I say we're just kind of looking to see. I can't tell you definitively because, I didn't do a quantitative test that tells me there's differences in cancer levels. But we didn't see any major differences between group to group from, disease indications or things like that.
I see. Yeah. Uh, what kinds of follow-up studies do you think?
Some of the studies that I think that I think are really important to do next is to really sort of define the dosing protocol and what how do we prepare now for clinical trials and anti-aging intervention? What studies do we need to do to get there? So, as one example, we only used female mice in the study. We did that for a specific reason, not because males or females per se, but we only had as pilot funding, and we didn't want to introduce another kind of confounding variable by having male and female. We don't know if there are sex specific differences. So we thought, let's just look at females for the time being. But that's another important question. Are there sex specific differences that impact efficacy? Um, are there optimal doses? What if we only gave 2 doses? Would you still have the same effect on survival? Um, does it impact maximal lifespan? Um, what does microdosing do? Uh, how about, if you started the equivalent of an 80-year-old person, would you have an impact? Or is there an age where beyond which point you don't see efficacy? Um, how many doses does it take to achieve efficacy? What's the optimal to achieve the maximal efficacy? So all of these kinds of things are things that need to be answered and investigated in order to bring to clinical trials. The other really important thing that needs to happen is monitoring for adverse effects, because I don't know, and I'm not aware of every study ever done, but most of them that give high dose in clinical trials, it's like 1 or 2 doses, maybe sometimes 3. I don't know of any study that's given, high doses over a period of years. So we don't know anything about the safety and potential for adverse effects of doing such a treatment regimen in patients. And so those types of things, I think we need to really monitor and test at the preclinical level to see if there are any indications of adverse effects. Is there an increased risk for cancer? There is some evidence out there that um, that psilocybin people have taken psilocybin. There's some published studies, and very, very, very few have decreased risk of cancer. Um, but that needs to be really closely monitored, especially alongside with this type of treatment regimen where you're giving it more as an aging um, agent versus you're giving it like once or depression or you know again the way that it's sort of been classically used in clinical trials. So we need to think about what tests are necessary at the preclinical level to identify optimal treatment protocols for clinical trials as an anti-aging therapeutic.
Yeah. I didn't know that there were studies that had looked at cancer and psilocybin and the relationship between them in humans.
They
Um,
But they were not like these studies where they looked at, well, let's give patients and we're gonna look at cancer. It's more like they evaluated people that have taken psilocybin in the past and people that haven't, and they found
yeah.
these correlations, associations. So
Mhm.
someone needs to really rigorously test this though. Giving psilocybin, especially at high doses, multiple times, and how that impacts the potential for adverse effects.
If we try to understand the effects of psilocybin and how they might, on a more zoomed out macroscopic level, result in slowed aging and possibly even reverse aging, like on the organismal level, then like chronic stress is an example of like a risk factor for aging, right? And we mentioned obesity as well, so metabolic dysfunction uh, is tightly related to that. And like, which of these major risk factors that are known to be related to aging processes would you say are most likely to be modulated by psilocybin?
Mm. Mm. Well, yeah, I mean, again, it's just one of these things that we don't know the answer yet. This is the first study to show these potent impacts systemically, and that
Yeah.
impact at all. So the next question is how? How is it working? What is it impacting at the systemic level? There's just so little known. Um, Again, and I realize now why. I mean, it's in part because it's a Schedule 1 drug, and there are things that that translate into research that make it challenging, like the iCook, approving something, but also regulatory barriers and challenges and things that take time, like just getting it into the lab and having access to it, along with the fact that um, it's challenging to get funding and federal funding. I mean, as an academic, the majority of my funding is typically federal. Uh, Not only are we in a tough time, federal funding for scientists in general, but traditionally, federal funding has not really been a huge supporter of this type of work. Um, and even just aging in general. So, aging is not a disease. A lot of people will say aging is not a disease. And so, it's tough to get research funding, even just to study anti aging versus an age related disease. So, there are a lot of sort of contributing things that are going to impact how much we know and how fast this moves forward.
Mm.
Thing from regulatory status to funding and barriers that we have in front of us as we try to do this research.
Yeah,
But
yeah,
the good news is that psilocybin has been the FDA has given this designated breakthrough therapy. So that's something that happens when you're trying to accelerate something through the FDA approval process more quickly. And that's a great sign because one, it underscores the safety profile, which the FDA would not give something breakthrough therapy designation unless it was very, very safe. So that's great. The other thing is it's in phase 3 clinical trials for a couple of different things right now. And so if it does get through phase 3 and it becomes FDA approved, and that changes one of the major categories that uh, of how we classify a Schedule One drug. One of the categories is that it has no accepted medical use. Well, if it becomes FDA approved, which seems like will happen in the near future, then it will have an accepted medical use, and I think it will be very quickly classified to a different schedule. So I think if and when, when that happens, that will loosen the challenges and the regulatory barriers that we face that will help to propel things moving forward.
yeah, yeah. How large were the lifespan? Well, in my study, then I shall say survival improving effects if we compare it with other drugs that have been studied for uh, slowing aging processes.
Yeah, that's a great question, and it's funny because I actually went back to all the really, really big and, aging studies, like with metformin and, calorie restriction or, other studies, and, um, the the short the short answer is I don't know, and the reason why is because if you really compare from study to study, they're all different, you know? I didn't see any of those studies where they started at 19 months of age and then went to 50%, survival. A lot of them started earlier or they gave different doses. So if they're giving this dose, how do you compare this dose to do this dose? The treatment initiation time, the frequency of treatment, the number of mice in the study. So I think between all of these variables, it's kind of like comparing apples to oranges. I think the right way to do it is to do those studies side by side where all the same variables are consistent. And then you really have a head to head comparison. I think that's the only way really to compare to other anti aging strategies out there.
Okay, okay. Um, because I was wondering, like, with the rise of AI and big data and so on, do you think that like computer models of the effects of various drugs on aging processes, for example, could be a way to start getting such comparisons done in some way? Like, I don't know the details of how this would be done, but like maybe that could be a starting point to generate more detailed hypotheses. What do you think about that?
Yeah, I mean, I feel like AI is doing more. We're doing more and more with AI literally daily. Every
Yeah.
day, new advancements with AI, it seems. So, I and I've used AI in my drug development projects in the past for different reasons. So, um, I'm sure there's someone out there that probably could do these types of modeling, maybe potentially. I don't know of a way personally right now. I think part of the issue is that this is one study, and this is the only study ever, and the only study out there that has shown anything about what psilocybin does in aging. So I think
Yeah.
tougher because AI really, what feeds AI is information that's out there.
Right.
And so with
Right.
such information, um, it'd be hard to make meaningful predictions. But I think that AI potentially could be used to help make more meaningful predictions, or maybe even help to design studies better, or maybe as more information comes out, more findings, people continuing to validate and make additional findings related to this. Maybe AI can can be more helpful in this process. I don't
Yeah.
know.
Yeah. Yeah. Um, and so while we're on the topic of big data, AI, and making large experiments with various geoprotective drugs, comparing their effects, like while we're on this topic of like having a lot of different research questions answered within experiments, like if you had unlimited resources, what research questions would you start trying to answer?
Yeah, I think the certainly all the ones that we've already talked about, relating to how do you do preclinical studies that can help define a dosing regimen for clinical trials. Even just looking at simple things like looking at dose dependence and frequency of dosing, and so what's the lowest dose that you can give to get the maximal benefit without causing adverse effects,
Yeah.
and defining that optimal treatment protocol that we can translate to patients, and evaluating the potential risks. Those are some of them. All of these things need to be validated, and having a bigger team to contribute to looking at, like, for example, if I were to do this study all over again, I would have an expert, a cardiac expert, a kidney expert, a liver expert, a cancer expert. I have an expert in every area that I can think of to monitor those things for their organ of interest, over the course of these experiments. I think that's gonna be really important.
Hmm. Yeah. What do you hope that your research, like what effects do you hope that your research has on society and well on the medical field?
Hmm. Um, well, from a big broad standpoint, I hope that, that younger people watching this video will see that being a scientist is an amazing job, an amazing profession, and that it's a job where, I feel very, very fortunate to be able to ask questions and go in the lab and answer them, and then publish exciting work and work with people all over the world to try to understand those findings better. And so I hope from a big picture perspective that the younger generation look at being a scientist as amazing career opportunity that that they can do. Uh, so there's that. I think I'm hoping that this research itself opens up a lot of doors in terms of people looking at psychedelics and psilocybin in a different way, and that it could have all of these incredible impacts outside the brain, and potentially in different organs, that it may have the potential to do a lot of beneficial things in terms of its potential for age-related disease, and that I hope people start exploring that as a new avenue. Um, Again, we just don't know enough about psilocybin. I'm realizing this is an amazing drug that has so much potential, and that we're just starting to uncover what its potential is. And it's a safe drug because, again, it's already been in so many clinical trials. So that's a really big benefit, I think, is that we know so much about the safety profile of this drug that has so many different disease indications. And we're just now starting to untap all the other things that it can do systemically. So I hope it opens a lot of doors and new frontier for new research to go down these types of paths and investigate things that haven't traditionally been investigated, with psilocybin. Um, and yeah, I just think it's interesting. Like, this is the natural substance from a mushroom that the earth has some medicines that are unexplored, and it's exciting to be able to have the opportunity to explore them.
Yeah, yeah, and the data are very fascinating as well. Yeah. As regards the because you started your career looking more at aging processes and fibrosis and oxidation, as you mentioned, what impact do you hope that your general focus on aging and the research you've done in this field will have?
Yeah, well, I think all scientists, like, we all hope that what we do matters. I think what we come in every day trying to do good science and drive things forward. And this particular finding has been really exciting and interesting to me because aging is something that we all are going to experience. It's something that is universal to everyone. And so it's exciting to work on something that is has such a broad impact, potentially. So yeah, it's exciting to just be in this space working on something that actually can have a meaningful impact because of the impact of aging. If we can find things that genuinely slow the aging process, and that's my goal. My goal isn't to help us live forever. I don't want to live forever. I don't think it's possible to live forever. Um, but I do think that it is scientifically possible to promote healthy aging in a better way or slow or delay the aging process. And my goal with my research is really not to try to find things that help you live forever, but to help you live healthier longer. And I think psilocybin has the potential to be one of those things.
Mm, mm. Yeah, yeah. Healthy aging indeed is like age is like as I just reflect on the medical rotations that we've had during the last couple of years, like it's probably the most like more than smoking, more than metabolic dysfunction and obesity. Like age is like for I want to say almost every, but maybe not, but like the majority of chronic diseases, it's a risk factor.
Yeah.
Uh,
Yeah,
yeah.
for fibrosis. And I mean, COVID is another example, right? Of it's like, so people who get COVID, it's all ages, but one of the big differences is that if you're older, your how the outcomes from COVID have been so much worse. And so with increasing age, you have these worse outcomes. And so if we have something potentially, and this is the big potential of something like this that we don't know the answer to yet, but if we have something that can slow that process and keep you phenotypically kind of younger, then that's that's the dream, is if we can do that. And then when you have an age related disease like COVID, maybe your body will react and behave and repair more like a young person. So that's kind of the ultimate, if we can find things that can do that. And so I think it'll be important to see, is psilocybin a drug that we do that? We need to test that
Right. Right.
across different age related diseases. COVID's one example because we all know that the older individuals have worse outcomes, but there are so many diseases where older individuals have worse outcomes.
Yeah. Yeah. Where can people learn more about what you're doing, maybe connect with you on social media and so on? Do you want to share your links?
Yeah, so I'm on LinkedIn, Louise Hecker, and I have a professional Twitter, which is at Hecker Louise. So people are welcome to follow me on there, and I post kind of updates on my publications and what I'm working on over there. So
Yeah.
people are welcome to contact me if they're interested in collaborating. I'm certainly always open to collaboration and like to involve people that have different disciplines, especially because, you know, instead of reinventing the wheel, I'd rather have collaborators that come in and, bring their expertise. And I always feel like research is more rich when you have different types of backgrounds all working on the same project. Because you don't need to be the expert at everything. You just need to include experts who have different expertise than you, and it's always a fun process for me to find all these interesting people doing cool stuff and develop collaborations. And
Yeah. Yeah, I agree with that philosophy, and it sounds uh, like very like you sound like you appreciate the people you work with, and that's probably a good thing to look for when looking for someone to work with. So I appreciate that. If listeners take away just one message from this conversation, what would you like that to be?
Hmm. Well, hmm. I guess uh, I guess if you're a scientist, that always think outside the box and explore new avenues, even if they seem off the wall. Follow the data, follow your passion, follow your interest, follow what you're interested in. Um, for kind of the general finding of this research, I think this is a new frontier in psilocybin research and its potential as a potential, uh, anti-aging agent. And so I think it's just the beginning. There's a lot more to come, and I hope this just serves as a starting point. And I'm excited to see where this goes.
Yeah, me too. Thank you for coming on the podcast, please.
Thank you.